Hello there and welcome to The Sleepy Astronaut, where the mysteries of space meet the comfort of curiosity. And tonight we're embarking on a journey that might just shatter everything you thought you knew about existence itself. We're diving into one of the most revolutionary ideas in modern physics, a theory so profound it could rewrite the very foundation of reality as we understand it. But before we venture into this cosmic rabbit hole, I'd love to know where in the universe you're watching from tonight and what questions about existence keep you awake at night, because what we're about to explore might just answer some of them in ways you never imagined. If you find this voyage through space and time as fascinating as I do, I'd be eternally grateful if you gave this video a like and perhaps subscribe to join our growing community of cosmic explorers. It helps this little corner of the internet reach other curious souls who might be searching for answers to the biggest questions in the universe. Now, I do hope this isn't so mind-bending that it keeps you awake all night, but if it does, well, at least you'll have learned something extraordinary about the nature of reality itself. So settle in, open your mind to possibilities that stretch beyond imagination, and let's begin this incredible journey. Because somewhere between what we think we know and what we're about to discover lies a truth so stunning it might change everything. Picture this for a moment. Everything you've ever been taught about the beginning of the universe, every textbook explanation, every documentary you've watched about the Big Bang, might be fundamentally wrong, not just slightly off, but completely upside down. What if the Big Bang wasn't the beginning at all, but rather something else entirely? Something that sounds like science fiction, but is grounded in the most rigorous mathematics and cutting-edge observations from our most powerful telescopes. Scientists are now proposing something that would have been laughed out of academic conferences just a decade ago. They're suggesting that our entire universe, everything we can see and touch and measure, every star and galaxy and particle of matter, might exist inside a black hole. Not orbiting around one, not being pulled toward one, but actually living our entire cosmic existence within the interior of a massive black hole that exists in some larger parent universe. This isn't the wild speculation of fringe theorists or the plot of a Hollywood blockbuster. This is serious science being proposed by respected physicists at major universities, backed by mathematical models that solve some of the biggest problems in cosmology, and supported by recent observations that have left astronomers scratching their heads and questioning everything they thought they understood about the cosmos. The story begins with a crisis in modern physics, a crisis so fundamental that it threatens to topple our entire understanding of how the universe works. For nearly a century, the Big Bang theory has been the cornerstone of cosmology, the grand narrative that explains how our universe came to be. According to this model, roughly 14 billion years ago, everything that exists was compressed into an infinitesimally small point called a singularity, a point of infinite density and temperature, where the laws of physics simply break down and cease to make any sense. But here's the problem that's been haunting physicists for decades. Singularities aren't just mysterious, they're mathematically impossible. When your equations produce infinity as an answer, it's not telling you something profound about the universe, it's telling you that your theory has failed. It's like dividing by zero, the mathematics simply falls apart. Yet, the Big Bang model requires us to accept that our entire universe emerged from just such an impossible mathematical object. This is where Polish theoretical physicist Nikodem Poplawski enters our story. Working at the University of New Haven, Poplawski has been developing a radical alternative that doesn't just tweak the Big Bang theory, but replaces it entirely with something far more elegant and, surprisingly, far more testable. His work is based on a modification of Einstein's general relativity called Einstein-Cartan theory, which takes into account a quantum property that Einstein's original equations ignored, the spin of particles. Now you might be wondering what particle spin has to do with the birth of the universe. It turns out quite a lot. In Einstein-Cartan theory, when particles with spin interact with the fabric of space-time, they create something called torsion. Think of space-time not as a flat sheet, but as a flexible rod that can be both bent and twisted. Einstein's relativity accounts for the bending, which we experience as gravity, But Einstein-Cartan theory also accounts for the twisting, the torsion, which becomes significant only under the most extreme conditions imaginable. This torsion acts as a kind of cosmic shock absorber. When matter becomes incredibly dense, approaching the point where traditional physics would predict a singularity, torsion kicks in and creates a repulsive force. Instead of matter collapsing to an impossible point of infinite density, it reaches a maximum compression and then bounces back, exploding outward in what Poplawski calls a big bounce, rather than a big bang. But here's where the story becomes truly extraordinary. This bounce doesn't happen in empty space. It happens inside a black hole, and the explosion that creates our universe emerges on the other side of that black hole's event horizon, connected by what physicists call an Einstein-Rosen bridge, more commonly known as a wormhole. In this model, every black hole is potentially a doorway to a new universe, and our universe itself exists within such a cosmic womb. This isn't just theoretical speculation anymore. Recent observations from the James Webb Space Telescope have provided what might be the first direct evidence supporting this revolutionary idea. When JWST turned its unprecedented gaze toward the distant universe, astronomers expected to find galaxies spinning in random directions, roughly half clockwise and half counterclockwise, just as you'd expect in a universe that began from a perfectly symmetric Big Bang. Instead, they found something that shouldn't exist according to traditional cosmology. Of the 263 spiral galaxies they analysed in their deep survey, approximately 60% rotate clockwise while only 40% rotate counterclockwise. This might not sound like much, but the statistical probability of this happening by pure chance is less than 0.07%. In scientific terms, this is what we call a smoking gun, evidence so compelling it demands explanation. This asymmetry directly violates what cosmologists call the cosmological principle, the fundamental assumption that the universe looks the same in all directions. So, if the Big Bang created our universe from a perfectly symmetric beginning, there should be no preferred direction of rotation for galaxies. But if our universe was born inside a rotating black hole, as Poplawski's theory suggests, then that rotation would leave its fingerprint on everything that formed afterward, including the galaxies we see today. Poplawski himself was thrilled by these findings. As he told reporters, it would be fascinating if our universe had a preferred axis. Such an axis could be naturally explained by the theory that our universe was born on the other side of the event horizon of a black hole existing in some parent universe. The discovery, if confirmed, would represent one of the most significant vindications of a revolutionary theory in the history of science. But the implications go far beyond just explaining why galaxies prefer to spin in one direction. This black hole universe model solves a host of problems that have plagued cosmology for decades. Remember those impossible singularities that break the laws of physics? Gone, replaced by a natural bounce mechanism that keeps matter at finite densities. The mysterious dark matter that supposedly makes up 80% of the universe but has never been directly detected. Potentially explained by the gravitational effects of torsion rather than invisible particles. The equally mysterious dark energy that's supposedly accelerating the expansion of the universe. The black hole model produces this acceleration naturally, without requiring exotic new forms of energy that exist nowhere else in physics. Even the cosmic inflation that supposedly stretched our universe to enormous size in its first fraction of a second finds a natural explanation in the bounce dynamics of the black hole interior. Perhaps most remarkably, this theory makes specific, testable predictions. Unlike many speculative ideas in physics, Poplawski's model tells us exactly what we should observe if it's correct. It predicts that our universe should have a slight positive curvature, meaning space is not perfectly flat, but curved like the surface of an enormous sphere. It predicts specific patterns in the cosmic microwave background radiation. And it predicts that the asymmetry in galaxy rotation should persist as we look deeper into space and further back in time. The European Space Agency's upcoming Euclid mission, designed to map the geometry of the universe with unprecedented precision, should be able to test many of these predictions directly. If Euclid finds evidence of positive curvature, it would be a powerful confirmation that we might indeed live inside a black hole. If it finds the universe to be perfectly flat, it would cast serious doubt on the theory. But perhaps the most mind-bending implication of this model is what it suggests about the nature of reality itself. If our universe exists inside a black hole, and if every black hole can potentially give birth to a new universe, then we're looking at an infinite hierarchy of nested realities. The black holes in our universe might each contain entire cosmos with their own galaxies, stars, planets, and perhaps even their own forms of life, completely unaware of the larger universe that contains them. At the same time, we might be inhabitants of just one branch in this cosmic tree, with countless parent universes extending infinitely upward, each containing the black hole that birthed the universe above it. It's a fractal reality where the very concept of ultimate origin becomes meaningless because there's always another layer, another parent universe, stretching back through an endless chain of cosmic births. This raises profound questions about the nature of existence itself. What would it mean for consciousness, for life, for meaning, if we discovered that our entire reality is just one bubble in an infinite foam of universes? Some philosophers argue it would make our existence more precious, not less, because we'd be part of an incredibly rare and beautiful phenomenon. Others suggest it might humble us in ways we can barely comprehend, forcing us to abandon the notion that our universe holds any special place in the grand scheme of things. But let's step back for a moment and examine what led scientists to even consider such a radical departure from established cosmology. The truth is, the Big Bang Theory, despite its widespread acceptance, has been accumulating problems like a cosmic snowball rolling downhill. Each new observation seems to require another patch, another exotic component to make the theory work. First came the realization that the universe is expanding faster than it should be, leading to the invention of dark energy, a mysterious force that supposedly makes up 68% of everything that exists, but has never been directly observed or understood. Then came the discovery that galaxies rotate too quickly to be held together by the matter we can see, leading to the hypothesis of dark matter, invisible particles that supposedly outweigh normal matter by a factor of 5-1, yet remain completely undetectable despite decades of increasingly sophisticated experiments. The cosmic microwave background radiation, the afterglow of the Big Bang, shows patterns that require yet another hypothetical mechanism called cosmic inflation, a period of faster-than-light expansion that supposedly occurred in the first tiny fraction of a second after creation. This inflation is driven by a hypothetical field that has never been observed and whose properties are adjusted specifically to match what we see in the sky. Then there's the Hubble tension, a growing crisis in cosmology where different methods of measuring the universe's expansion rate give contradictory results. Some measurements suggest the universe is expanding at 67 kilometers per second per megaparsec, while others indicate 74 kilometers per second per megaparsec. This might sound like a small difference, but in cosmology it's enormous, suggesting that something fundamental is wrong with our understanding. Meanwhile, the James Webb Space Telescope has been delivering observation after observation that doesn't quite fit the standard model. Galaxies that appear too massive and too mature for their supposed age. Structures that seem too large to have formed in the time available since the Big Bang. Stars that appear older than the universe itself. Each discovery requires creative explanations that strain the credibility of the overall framework. It's against this backdrop of mounting problems that Poplawski's black hole universe theory emerges not as wild speculation, but as a potential solution to multiple crises simultaneously. The theory doesn't require dark matter, dark energy, or cosmic inflation, because the dynamics of the black hole interior naturally produce the effects we observe. The Hubble tension disappears because the expansion history of a universe born from a black hole collapse follows different mathematics than a Big Bang universe. The recent research from the University of Portsmouth has provided additional mathematical rigor to these ideas. Professor Enrique Gastenaga and his colleagues have shown that gravitational collapse in Einstein-Cartan theory doesn't end in a singularity, but in a bounce that creates a new expanding universe. Their calculations demonstrate that this bounce occurs entirely within the framework of established physics, requiring no exotic new fields or particles. What emerges from their mathematics is a universe that looks remarkably like our own. The bounce naturally produces the two phases of accelerated expansion that we observe. An early rapid expansion similar to cosmic inflation, followed by the current accelerating expansion attributed to dark energy. But in their model, both phases arise from the same underlying physics of the gravitational bounce, elegant in its simplicity. The theory also addresses one of the most profound mysteries in physics. Why does time have a direction? In most fundamental equations, time is symmetric, meaning they work equally well running forward or backward. Yet we experience a clear arrow of time, flowing from past to future. In the black hole universe model, this arrow is inherited from the parent universe through the rotation of the black hole that birthed our cosmos. The motion of matter through the black hole's event horizon can only happen in one direction, providing a fundamental asymmetry that propagates throughout the daughter universe. This connection between parent and child universes isn't just mathematical abstraction, it suggests that information, in some form, passes from one universe to the next. The rotation rate of the parent black hole influences the properties of the child universe. The amount of matter that collapsed to form the black hole determines the size and expansion rate of the new cosmos. In a sense, universes inherit characteristics from their parents, like cosmic DNA passing from generation to generation. But how could we ever hope to test such extraordinary claims? The beauty of Poplawski's theory lies in its testability. Unlike string theory or many other speculative ideas in physics, the black hole universe model makes specific predictions that can be verified or falsified by observation. We've already seen the first potential confirmation in the JWST galaxy rotation data, but there are many more tests to come. The theory predicts that our universe should have a small but measurable positive curvature, meaning that if you could somehow travel in a straight line long enough, you would eventually return to your starting point, like an ant walking around the surface of a balloon. The upcoming Euclid mission will measure this curvature with unprecedented precision. If it finds positive curvature, it would be strong evidence for the black hole origin. If it finds perfect flatness, the theory would face serious challenges. The model also predicts specific patterns in the cosmic microwave background radiation that differ subtly from those expected in a Big Bang universe. Future missions designed to study this ancient light in ever greater detail should be able to distinguish between the two scenarios. The theory even predicts that we might be able to detect gravitational waves from the original bounce, though this would require detector technology far beyond our current capabilities. Perhaps most intriguingly, the theory suggests that we might be able to learn something about the parent universe that contains us. The properties of our cosmos, from the strength of gravity to the masses of fundamental particles, might encode information about the black hole from which we emerged. By studying our own universe in sufficient detail, we might be able to infer characteristics of the larger reality that contains us, like archaeologists reconstructing an ancient civilization from fragments of pottery. This raises fascinating questions about communication between universes. If information can pass from parent to child through the black hole formation process, might it be possible to send messages the other way? Could an advanced civilization somehow encode information in the matter that falls into a black hole, knowing that it would influence the properties of any universe that emerges? These questions push the boundaries of what we can even imagine, let alone test, but they highlight the profound implications of taking the black hole universe theory seriously. The resistance to such radical ideas within the scientific community is understandable. Science progresses through careful accumulation of evidence, and extraordinary claims require extraordinary proof. Many physicists remain skeptical of the black hole universe model, arguing that it's too early to abandon the Big Bang theory based on limited observations. They point out that the galaxy rotation asymmetry observed by JBUST, while intriguing, could have other explanations that don't require such a dramatic revision of cosmology. Some suggest that the asymmetry could result from systematic biases in how we measure distant galaxies, perhaps related to our own galaxy's motion through space, or subtle effects in how the James Webb Telescope processes light from rotating objects. Others propose that the pattern could be a statistical fluke that will disappear as we observe more galaxies, though the probability of this becomes increasingly small with each new observation that confirms the trend. Yet the mounting evidence continues to challenge conventional wisdom in ways that feel increasingly difficult to dismiss. The Hubble tension persists despite decades of refinement in measurement techniques. Dark matter particles remain stubbornly undetectable despite experiments of ever-increasing sensitivity. The cosmic microwave background radiation shows anomalies that require increasingly creative explanations within the standard model. Each problem might be solvable individually, but together they paint a picture of a theory under strain. This is where the black hole universe model begins to shine not just as an alternative explanation, but as a unifying framework that addresses multiple mysteries simultaneously. Consider the profound elegance of a theory that explains cosmic inflation, dark energy, the arrow of time, and galactic rotation asymmetry through a single mechanism, the dynamics of gravitational collapse and rebound within a rotating black hole. It's the kind of theoretical beauty that has historically guided physics toward its greatest breakthroughs. The mathematics underlying this model reveals layers of complexity that continue to surprise researchers. Recent work has shown that the torsion effects in Einstein-Cartan theory don't just prevent singularities, they create a natural mechanism for generating the quantum fluctuations that seed galaxy formation. In the standard Big Bang model, these fluctuations must be inserted by hand through the cosmic inflation mechanism. In the black hole universe, they emerge naturally from the quantum properties of matter undergoing extreme compression and rebound. This quantum dimension adds another fascinating aspect to the theory. The boundary between our universe and the parent black hole isn't a simple geometric surface, but a quantum interface, where the laws of physics themselves undergo a kind of transformation. Matter crossing this boundary doesn't simply fall into our universe, it undergoes a fundamental change in its relationship to space and time. The very concepts of inside and outside become fluid, existing in a quantum superposition until the moment of observation. Professor Gastanaga's team at the University of Portsmouth has been exploring these quantum aspects in greater detail, developing mathematical models that describe how information and energy flow through the black hole boundary. Their work suggests that the process isn't random, but follows specific rules that determine what kinds of universes can emerge from what kinds of black holes. Not every black hole births a cosmos like ours. Some might produce universes with different physical laws, different numbers of dimensions, or even different relationships between matter and energy. This raises the tantalizing possibility that our universe's properties, the things we take as fundamental constants like the speed of light or the strength of gravity, might actually be contingent features inherited from our parent black hole. In other universes born from different black holes, these constants might have different values, leading to cosmos where stars burn differently, atoms bond in unfamiliar ways, or time itself flows at a different rate. The implications for our understanding of physics are staggering. If the fundamental constants aren't truly fundamental but are instead inherited characteristics, then much of what we consider immutable about reality becomes variable. The anthropic principle, which suggests that our universe's properties are fine-tuned for life because we exist to observe them, transforms into something more dynamic. Perhaps life finds a way to emerge in any universe that persists long enough, adapting to whatever physical laws it inherits from its cosmic parent. This adaptive view of cosmic evolution opens up new ways of thinking about the relationship between physics and biology. In a multiverse where each black hole spawns a new universe with slightly different properties, natural selection might operate not just on organisms within a single cosmos, but on the universes themselves. cosmos that produce conditions favorable to complexity, structure formation, and eventually life might be more likely to generate the massive stars that collapse into black holes, thus propagating their physical laws to daughter universes. The concept challenges our deepest assumptions about causality and purpose in the universe. If our cosmos exists within a vast hierarchy of nested realities, then the question of ultimate origin becomes not just difficult to answer, but possibly meaningless. There might be no first universe, no ultimate beginning, just an eternal process of cosmic birth and evolution, stretching infinitely in all directions through dimensions of reality we can barely conceptualize. Yet this infinite regression doesn't necessarily lead to nihilism or meaninglessness. Instead, it might point toward a universe that is inherently creative, constantly generating new forms of complexity and beauty. Each black hole becomes a seed of possibility, each universe a unique experiment in the laws of physics. We might be living not in a cosmos that emerged from nothing, but in one branch of an infinite tree of reality, each branch exploring different ways that matter, energy, space, and time can dance together. The observational tests of this theory continue to multiply as our instruments become more sophisticated. The European Space Agency's Euclid mission, launching to map the geometry of space-time itself, will provide crucial measurements of cosmic curvature. The Nancy Grace Roman Space Telescope will survey billions of galaxies with unprecedented precision, allowing us to test whether the rotation asymmetry holds across all scales and epochs. Ground-based observatories are being designed to detect the gravitational wave signatures that might echo from the original bounce that birthed our universe. Perhaps most excitingly, the theory predicts that we might be able to identify black holes in our own universe that are actively giving birth to new cosmos. These wouldn't look different from ordinary black holes to external observers, but their internal dynamics would be creating entirely new realities on the other side of their event horizons. Every time we observe matter falling into a black hole, we might be witnessing the raw material for a new universe, complete with its own space, time, and physical laws. The philosophical implications ripple outward like waves from a cosmic stone thrown into the pond of reality. If consciousness can emerge in our universe, it can presumably emerge in others. There might be infinite numbers of aware beings scattered across the hierarchy of nested realities, each grappling with the same fundamental questions about existence, meaning, and their place in the grand scheme of things. Some might be asking the same questions we're exploring right now, wondering if their universe exists inside a black hole, unaware that countless others are doing the same. This vision of reality as an infinite flowering of consciousness and complexity offers a kind of cosmic democracy, where no single universe, including ours, holds a privileged position. We're all participants in the same vast experiment, each universe contributing its own unique perspective to the totality of existence. The black holes we fear as cosmic destroyers might actually be cosmic creators, the very mechanisms by which reality perpetuates and explores itself. The technical challenges of testing these ideas push the boundaries of what's possible with current technology. Measuring the curvature of space requires precision that approaches the fundamental limits imposed by quantum mechanics. Detecting gravitational waves from cosmic bounces would require instruments sensitive enough to feel the ripples from events that occurred billions of years ago, across distances that strain comprehension. Confirming the galaxy rotation asymmetry demands surveys of millions of objects scattered across the observable universe. Yet each of these challenges represents an opportunity for technological advancement that could benefit far more than just cosmology. The precision timing systems needed for gravitational wave detection have already revolutionized global positioning systems. The sensitive detectors required for dark matter searches have found applications in medical imaging and national security. The computational techniques developed to analyze cosmic surveys are being applied to problems ranging from climate modeling to artificial intelligence. The black hole universe theory thus represents more than just an alternative cosmological model. It embodies a new way of thinking about the relationship between observation, theory, and reality itself. It suggests that the universe might be far stranger and more wonderful than our current models indicate, while simultaneously being more testable and concrete than many speculative alternatives. It grounds wild cosmic possibilities in rigorous mathematics while opening up vistas of reality that stretch the imagination. As we stand on the threshold of a new era in observational cosmology, with instruments capable of peering deeper into space and further back in time than ever before, we might be about to witness one of the great revolutions in human understanding. The question isn't just whether we live inside a black hole, but what it would mean for our understanding of existence, consciousness, and our place in the infinite hierarchy of reality if we do. The evidence continues to accumulate, each new observation adding another piece to a puzzle that grows more fascinating with every discovery. Whether Poplaski's revolutionary theory ultimately proves correct or leads us towards some even more extraordinary understanding of reality. One thing seems certain: we're living through a time when the very foundations of cosmology are being questioned, tested, and potentially transformed. The universe, it seems, still has surprises in store for us, and the biggest surprise of all might be that everything we thought we knew about our cosmic origins was just the beginning of a much larger and more beautiful story. The story becomes even more compelling when we consider the mathematical elegance that emerges from this radical rethinking of cosmic origins. Unlike the patchwork of exotic components that the Big Bang model requires, the black hole universe theory flows from a single, coherent framework. It's like replacing a complex machine held together with duct tape and hope with a Swiss watch where every component serves a purpose and contributes to the whole. This mathematical beauty isn't just aesthetically pleasing, it's historically been one of the most reliable guides to scientific truth. When Einstein formulated his theory of relativity, it wasn't because he had overwhelming experimental evidence, it was because the mathematics possessed an undeniable elegance that suggested deep truth about the nature of reality. The same quality emerges from Poplaski's equations, a sense that the universe might actually work this way because it's so much more natural than the alternatives. But let's delve deeper into what this theory suggests about the very nature of space and time. In the traditional Big Bang model, space-time simply begins at the moment of creation, emerging from nothing like a cosmic magic trick. But in the black hole universe model, space-time has a genealogy, a family tree that extends backward through parent universes in an endless chain of cosmic inheritance. This genealogical view of reality transforms our understanding of physical laws themselves. The speed of light, the strength of gravity, the masses of particles, all these supposedly fundamental constants might actually be inherited traits passed down from parent to child universe through the black hole birth process. It's as if each universe receives a cosmic DNA that determines its basic properties, and this DNA carries the accumulated history of countless previous generations of reality. The implications cascade through every aspect of physics. Quantum mechanics, with its probabilistic nature and observer effects, might not be fundamental features of reality, but emergent properties that arise from the interface between parent and child universes. The wave function collapse that occurs when we make a measurement might reflect the quantum uncertainty inherent in crossing the boundary between different levels of reality. Even more fascinating is what this suggests about the relationship between consciousness and cosmos. If awareness can emerge in our universe, and if our universe is just one branch in an infinite tree of realities, then consciousness might be far more prevalent in the multiverse than we ever imagined. There could be forms of awareness scattered throughout the hierarchy of nested universes, each experiencing reality from their own unique perspective within their own cosmic bubble. Some of these conscious beings might have already discovered their own black hole origins and might be grappling with the same questions that we're exploring. Others might exist in universes so different from ours that their forms of awareness are completely alien to anything we can imagine. Yet all would share the common heritage of being products of the same fundamental process: the eternal dance of collapse and rebound that creates new realities from the ashes of old ones. This raises profound questions about communication and connection across the cosmic hierarchy. While we can't directly observe parent universes or communicate with them in any conventional sense, the theory suggests that information does flow between levels of reality through the black hole formation process. The properties of our universe encode information about the black hole that birthed us, which in turn carries information about the parent universe that contained that black hole. In principle, a sufficiently advanced civilization might be able to decode this cosmic ancestry, reading the history of parent universes in the fundamental constants and physical laws of their own reality. They might even be able to influence daughter universes by carefully controlling what falls into the black holes in their cosmos, essentially programming the initial conditions for new realities. The technical challenges of exploring these ideas push us toward revolutionary advances in observational astronomy and theoretical physics. The European Space Agency's upcoming missions will test the theory's predictions with unprecedented precision, while new generations of gravitational wave detectors might eventually become sensitive enough to hear the echoes of cosmic bounces from the dawn of time. But perhaps the most intriguing tests will come from studying black holes themselves. If every black hole is potentially giving birth to a new universe, then the dynamics of matter falling across event horizons takes on cosmic significance. We're not just watching material disappear from our reality, we're witnessing the raw ingredients for entirely new forms of existence. Advanced computer simulations are beginning to model these processes in extraordinary detail, following matter as it crosses the event horizon and undergoes the torsion-driven bounce that creates new space-time. These simulations suggest that the process isn't random but follows specific patterns that determine what kinds of universes emerge from what kinds of collapses. The results are stunning in their implications. Not every collapse produces a universe like ours. Some might create realities where time flows differently, where space has more or fewer dimensions, where the relationship between matter and energy follows completely different rules. The multiverse that emerges from this process isn't just vast in size, but infinite in its creative possibilities. This diversity of possible universes provides a natural explanation for why our cosmos seems so perfectly suited for complexity and life. We're not observing a universe that was fine-tuned by some external agency. We're inhabiting one member of an infinite ensemble where every possible combination of physical laws gets explored. In such a multiverse, universes like ours, capable of producing stars, planets, and eventually life, are inevitable simply because every possibility gets tried. The anthropic principle transforms from a puzzle about cosmic fine-tuning into a natural consequence of infinite cosmic evolution. We observe a universe suitable for life not because it was designed for us, but because we're the inevitable result of a process that explores every possible way that reality can organize itself. Yet this doesn't diminish the wonder and significance of our existence. If anything, it enhances it by placing us within a cosmic story of literally infinite scope and creativity. Every moment of consciousness, every act of discovery, every expression of love and beauty becomes part of an eternal flowering of awareness that spans all possible realities. The philosophical implications continue to unfold like an origami universe, revealing new layers of complexity with each fold. If consciousness is a natural emergent property of sufficiently complex systems, and if the multiverse contains infinite variations on the theme of cosmic evolution, then awareness might be the universe's way of experiencing itself from every possible perspective. We might be living not in a dead mechanical cosmos, but in something more akin to a vast mind exploring its own possibilities through the experiences of countless conscious beings scattered across infinite realities. Each thought, each moment of wonder, each scientific discovery becomes a neuron firing in this cosmic consciousness, contributing to an understanding that spans all possible worlds. The recursive nature of this vision is breathtaking. Conscious beings within each universe study their reality and discover that they exist within black holes in larger universes, which themselves contain conscious beings making the same discoveries about their own cosmic origins. It's an infinite hall of mirrors where every reflection contains the same fundamental truth seen from a different angle. This raises questions about the ultimate nature of existence that push beyond the boundaries of science into philosophy and perhaps even spirituality. If reality is truly infinite in scope, containing every possible variation on the themes of space, time, matter, and consciousness, then what does it mean to ask about ultimate origins or final purposes? Perhaps the question itself reveals a limitation in how we think about existence. In a truly infinite multiverse, there might be no ultimate beginning or final end, just an eternal process of becoming that explores every possible way that reality can manifest itself. We're not products of a single creative act, but participants in an ongoing cosmic improvisation that never repeats itself and never comes to an end. The practical implications of these ideas continue to ripple through multiple fields of science and technology. Understanding torsion effects in extreme gravitational fields could revolutionize our approach to space propulsion and energy generation. If we could harness even a tiny fraction of the forces that drive cosmic bounces, we might be able to manipulate space-time itself in ways that seem impossible with current technology. The mathematical techniques developed to model universe formation within black holes are already finding applications in other areas of physics, from plasma dynamics to condensed matter systems. The computational methods needed to simulate cosmic bounces are pushing the boundaries of what's possible with supercomputers and quantum computing systems. Perhaps most significantly, the theory is inspiring new approaches to the fundamental problem of unifying quantum mechanics with general relativity. By showing how torsion can bridge the gap between the microscopic quantum world and the macroscopic realm of gravity, Poplaski's work points toward a more complete theory of quantum gravity that might finally reconcile these two pillars of modern physics. The observational campaigns now underway to test these ideas represent some of the most ambitious projects in the history of astronomy. Teams of researchers are analysing data from multiple space telescopes, looking for subtle signatures that could distinguish between different models of cosmic origins. The statistical techniques required to extract meaningful signals from cosmic noise are advancing the entire field of data science. Meanwhile, theorists continue to refine and extend the mathematical framework, exploring what kinds of universes could emerge from different types of black hole collapses. The diversity they're discovering is staggering, with possibilities ranging from universes where time runs backward to realities where space has fractal geometry to cosmos, where the very concept of particles and fields takes on completely alien forms. Each new theoretical possibility suggests new observational tests, creating a virtuous cycle where theory and experiment push each other toward ever deeper understanding. We're witnessing the birth of a new kind of cosmology, one that embraces the infinite creativity of nature while remaining grounded in rigorous mathematical analysis and empirical testing. The cultural impact of these ideas extends far beyond the scientific community. Artists, writers, and philosophers are beginning to grapple with the implications of living in an infinite hierarchy of nested realities. The vision of cosmic creativity on an unlimited scale is inspiring new forms of artistic expression and challenging traditional assumptions about meaning and purpose in human life. Educational institutions are beginning to incorporate these ideas into their curricula, preparing students for a future where our understanding of reality might be radically different from what previous generations took for granted. The interdisciplinary nature of the research is breaking down traditional boundaries between physics, astronomy, mathematics, computer science, and philosophy. Yet for all its cosmic scope and revolutionary implications, the black hole universe theory remains grounded in the fundamental scientific principle of testability. Unlike many speculative ideas about the nature of reality, this framework makes specific predictions that can be verified or falsified through observation. The next decade of astronomical discovery will likely determine whether this radical vision of cosmic origins can withstand the scrutiny of empirical testing. The stakes couldn't be higher. If the theory proves correct, it will represent one of the greatest revolutions in human understanding since Copernicus displaced Earth from the center of the cosmos. If it proves incorrect, it will still have served the valuable purpose of pushing our thinking about fundamental questions and inspiring new approaches to cosmic mysteries. Either way, we're living through a remarkable moment in the history of human knowledge, a time when our most basic assumptions about existence are being questioned and potentially transformed. The universe continues to surprise us, revealing layers of complexity and beauty that exceed our wildest imaginations, while remaining amenable to rational investigation and mathematical description. As we stand on the threshold of discoveries that could reshape our understanding of everything from the nature of time to the meaning of consciousness, one thing becomes clear: the cosmic story is far from over. We're not just observers of this magnificent tapestry of nested realities. We're active participants in its ongoing creation, each moment of awareness and discovery adding new threads to a pattern that grows more beautiful and complex with every passing moment. The journey into the depths of cosmic mystery continues, carrying us toward revelations that might prove even more extraordinary than living inside a black hole. In a universe where anything is possible and everything eventually happens, the greatest discoveries might still lie ahead, waiting to transform our understanding of what it means to exist in this strange and wonderful reality we call home. The journey through cosmic possibility takes another fascinating turn when we consider the profound silence that surrounds us in the night sky. If the black hole universe theory is correct, and if consciousness emerges naturally in cosmos like ours, then we should expect to find evidence of other civilizations scattered throughout our reality. Yet despite decades of searching, we've found nothing but cosmic quiet. This absence itself might be telling us something profound about the nature of reality and our place within it. Consider the implications of existing within a black hole hierarchy where information can only flow in one direction, from parent to child universe. Any civilization that achieves sufficient technological mastery might eventually discover their cosmic origins and realize that they can influence the properties of daughter universes through careful manipulation of black hole formation. This raises the tantalizing possibility that our universe's seemingly fine-tuned properties aren't accidents of cosmic evolution, but deliberate choices made by advanced beings in the parent reality. The idea sounds like science fiction, but the mathematics is surprisingly concrete. If torsion effects allow information to pass through the black hole boundary during universe formation, then the composition and dynamics of collapsing matter could serve as a kind of cosmic programming language. An advanced civilization might encode specific instructions into the material that falls into black holes, knowing that these instructions would influence the fundamental constants and physical laws of any universe that emerges. This perspective transforms every black hole in our cosmos into something far more significant than a mere gravitational anomaly. They become potential wombs of reality, cosmic nurseries where new forms of existence are being born according to patterns that might have been established by conscious design. The supermassive black holes at the centers of galaxies, feeding on surrounding matter and growing ever larger, could be gestating entire universes whose properties reflect the intentions and wisdom of their cosmic parents. But this raises unsettling questions about our own cosmic heritage. If our universe was indeed born from a black hole in a parent reality, what does that suggest about the beings who might have influenced our creation? Are we living in a cosmos that was deliberately designed to produce complexity, consciousness, and perhaps specific forms of life? Or are we the products of a more random process, one branch among countless variations being explored by an infinitely creative multiverse? The search for answers leads us into territory where science begins to merge with philosophy and perhaps even theology. If our physical constants were chosen by advanced beings in a parent universe, then those beings occupy a position that previous generations might have reserved for divine entities. They would be our creators in the most literal sense, though they themselves would presumably be the products of even earlier cosmic generations stretching back through an infinite hierarchy. This infinite regression eliminates the need for any ultimate creator, while still allowing for conscious design at every level of reality. Each universe could be both created and creator, designed by its parents and designing its children in an endless chain of cosmic responsibility. The theological implications are staggering, suggesting a form of distributed divinity where godlike power emerges naturally from sufficient technological advancement and cosmic understanding. Yet the theory also suggests profound humility about our place in this hierarchy. If we exist within a black hole, then our entire observable universe represents just the interior of a single object in the parent reality. Everything we can see from the nearest star to the most distant galaxy would fit within what appears to external observers as an ordinary black hole, possibly no more significant to them than the black holes in our own sky are to us. This nested perspective on cosmic scale challenges our deepest intuitions about size and significance. The vast expanses of space that inspire awe and wonder when we contemplate them might be cosmically insignificant, mere details within a structure that occupies a tiny portion of a much larger reality. Yet this doesn't diminish the importance of our existence or the meaning of our discoveries. If anything, it highlights the incredible richness that can emerge from even the smallest seeds of possibility. The mathematical framework underlying these ideas continues to reveal new layers of complexity as researchers probe deeper into its implications. Recent work has shown that the torsion effects responsible for preventing singularities also create natural mechanisms for generating the quantum fluctuations that seed structure formation. This means that the same physics that prevents our universe from collapsing into mathematical impossibility also ensures that it develops the complex patterns we observe in galaxies, stars, and planets. The elegance of this connection suggests something profound about the relationship between mathematical beauty and physical reality. It's as if the universe is constructed according to principles that naturally produce both stability and complexity, order and creativity, mathematical consistency and experiential richness. This isn't the mechanical clockwork cosmos that earlier generations imagined, but something more akin to a vast improvisation where fundamental rules create space for infinite variation and surprise. The observational consequences of this framework continue to unfold as our instruments become more sophisticated. The Vera Rubin Observatory, currently under construction, will survey the entire visible sky repeatedly, creating a time-lapse movie of cosmic evolution that could reveal subtle patterns consistent with black hole universe origins. The data from this survey will be so vast that artificial intelligence systems are being developed specifically to search for signals that human analysts might miss. Meanwhile, gravitational wave detectors are being upgraded to detect ever more subtle ripples in space-time. If our universe truly began with a cosmic bounce rather than a big bang, then the gravitational waves from that primordial event might still be echoing through the cosmos, carrying information about the conditions that prevailed during our cosmic birth. Detecting these ancient signals would provide direct evidence of the bounce mechanism and potentially reveal details about the parent black hole that created us. The technological challenges are immense, requiring detector sensitivity that pushes against the fundamental limits imposed by quantum mechanics. The instruments needed to detect primordial gravitational waves must be isolated from every possible source of vibration, from earthquakes to passing trucks to the thermal motion of atoms in the detector materials themselves. Yet the potential payoff justifies these extraordinary efforts. A success would provide our first direct glimpse into the moment of cosmic creation. Parallel efforts are underway to search for other signatures of the black hole universe model in the cosmic microwave background radiation. This ancient light, which has been traveling through space for nearly 14 billion years, carries encoded information about the conditions that prevailed when our universe was just a few 100,000 years old. Subtle patterns in this radiation could distinguish between different models of cosmic origins, potentially providing definitive evidence for or against the black hole universe theory. The precision required for these measurements is extraordinary, demanding instruments capable of detecting temperature variations of a few millionths of a degree across the sky. The data analysis requires supercomputers working for months to extract meaningful signals from cosmic noise. Yet each new measurement brings us closer to understanding whether our universe truly began with a bounce inside a black hole, or whether some other mechanism was responsible for our cosmic origins. The implications extend far beyond cosmology into the deepest questions about the nature of existence itself. If consciousness can emerge in our universe, and if our universe is just one bubble in an infinite foam of realities, then awareness might be far more prevalent in the multiverse than we've ever imagined. There could be countless forms of conscious experience scattered throughout the hierarchy of nested universes, each exploring reality from their own unique perspective. Some of these conscious beings might exist in universes with physical laws so different from ours that their forms of awareness are completely alien to anything we can conceive. Others might inhabit realities where consciousness itself takes on forms that transcend individual minds, perhaps existing as collective entities that span entire galaxies or as distributed intelligences woven into the fabric of space-time itself. The recursive nature of this vision creates a kind of cosmic democracy, where every possible form of awareness gets its chance to experience reality. In an infinite multiverse that explores every possible combination of physical laws and initial conditions, every way that consciousness can emerge and evolve eventually gets tried. We're not special because we're the only conscious beings in existence, but because we represent one unique perspective in an infinite symphony of awareness. This transforms our understanding of loneliness and cosmic significance. The apparent silence of our night sky might not indicate that we're alone in the universe, but that we're part of a much larger community of conscious beings scattered across multiple levels of reality. The civilizations we're searching for might exist not in distant galaxies within our own universe, but in parallel realities accessible only through the black hole boundaries that separate different levels of the cosmic hierarchy. The search for extraterrestrial intelligence takes on new dimensions when viewed through this lens. Rather than looking only for radio signals from distant stars, we might need to search for evidence of cosmic engineering projects that span multiple universes. Advanced civilizations might leave their signatures not in electromagnetic radiation, but in the fundamental constants and physical laws of the realities they help create through black hole manipulation. The technological implications of these ideas stretch the imagination beyond current limits. If we could somehow learn to manipulate torsion effects in strong gravitational fields, we might be able to influence the properties of universes that emerge from black holes in our own cosmos. This would represent a form of cosmic parenthood where we take responsibility for the realities we help bring into existence. The ethical implications are staggering. If we have the power to influence the fundamental properties of new universes, what responsibilities does that create? Should we try to optimize the physical constants for complexity and consciousness, ensuring that our daughter universes have the best possible chance of developing life and awareness? Or should we allow the process to unfold naturally, respecting the autonomy of whatever conscious beings might eventually emerge? These questions push beyond traditional ethics into territory where we must consider our obligations to beings who don't yet exist and might never exist in forms we can recognize. The moral framework for cosmic parenthood has no precedent in human experience, yet it might become one of the most important challenges facing any civilization that achieves sufficient technological mastery. The mathematical tools needed to explore these possibilities are advancing rapidly, driven by the intersection of theoretical physics, computer science, and artificial intelligence. Machine learning systems are being trained to recognize patterns in cosmic data that might reveal signatures of black hole universe origins. Quantum computers are being developed to simulate the complex dynamics of matter undergoing torsion-driven bounces. The computational challenges are enormous, but so are the potential rewards. Each new calculation reveals additional layers of complexity in the black hole universe model. The process of cosmic birth turns out to be far richer than initially imagined, with multiple phases of evolution that determine different aspects of the emerging reality. The early moments after the bounce establish the fundamental constants and physical laws. Later phases determine the large-scale structure and the seeds of complexity that will eventually give rise to galaxies, stars, and planets. The interplay between these different phases creates a kind of cosmic genetics where the properties of parent universes influence their offspring in subtle but profound ways. Just as biological evolution passes traits from generation to generation while allowing for variation and adaptation, cosmic evolution might follow similar patterns on scales that dwarf anything we've previously imagined. The cultural impact of these ideas continues to ripple through society, inspiring new forms of art, literature, and philosophical inquiry. Writers are exploring what it might mean to live in a universe with cosmic parents, while artists are creating works that capture the infinite recursion of nested realities. Philosophers are grappling with questions about identity and meaning in a cosmos where every possible variation on existence eventually gets explored. Religious traditions are beginning to engage with the implications of distributed creation, where godlike power emerges naturally from cosmic evolution rather than existing as an external force. Some find in these ideas a new form of spirituality that embraces both scientific rigor and cosmic wonder. Others see challenges to traditional beliefs that require careful theological consideration. Educational institutions are struggling to keep pace with rapidly evolving ideas that challenge fundamental assumptions about reality. Students today might need to be prepared for a future where our understanding of existence has been radically transformed by discoveries that haven't yet been made. The interdisciplinary nature of these questions is breaking down traditional academic boundaries and creating new fields of study that combine physics, philosophy, computer science, and even theology. The timeline for testing these revolutionary ideas continues to accelerate as new missions are planned and launched. The European Space Agency's Euclid mission will provide crucial measurements of cosmic curvature within the next few years. The James Webb Space Telescope continues to survey distant galaxies, potentially providing additional evidence of rotation asymmetries that support the black hole universe model. Ground-based observatories are being upgraded to detect ever more subtle signals that might reveal our cosmic origins. Each new observation carries the potential to either support or refute this radical vision of reality. The scientific process continues its relentless march toward truth, testing extraordinary claims against extraordinary evidence. Whether the black hole universe theory ultimately proves correct or leads toward even more surprising discoveries, we're living through a time when humanity's understanding of existence itself hangs in the balance. The stakes extend far beyond academic curiosity into questions about the future of human civilization and our role in the cosmic hierarchy. If we truly exist within a black hole, and if we eventually develop the technology to influence the birth of new universes, then we face responsibilities that previous generations could never have imagined. We might not just be observers of cosmic evolution, but active participants in shaping the future of reality itself. The journey toward understanding continues, carrying us deeper into mysteries that challenge every assumption about existence, consciousness, and our place in the infinite tapestry of nested realities. Each discovery opens new questions. Each answer reveals new horizons of possibility. The universe, it seems, has reserves of wonder that exceed even our most ambitious imaginations, and the greatest revelations might still lie ahead, waiting to transform everything we think we know about what it means to exist in this strange and magnificent reality we call home. As we reach the end of our cosmic journey tonight, we find ourselves standing at the edge of perhaps the most profound realization in human history. The evidence continues to mount, each observation from our most powerful telescopes adding weight to a possibility that would have been dismissed as pure fantasy just decades ago. We might not be living in the universe we thought we were, but rather existing as inhabitants of a cosmic interior, our entire reality nestled within the event horizon of a massive black hole in some unimaginably vast parent cosmos. The implications ripple through every aspect of human understanding, like waves through still water. If this theory proves correct, then every sunrise you've ever witnessed, every star that's guided explorers across ancient oceans, every galaxy that's inspired wonder in the hearts of astronomers, all of it exists within what appears to external observers as a single, relatively ordinary black hole. The scale is both humbling and breathtaking, suggesting that the universe has layers of magnificence that dwarf even our most ambitious attempts at cosmic poetry. But perhaps the most beautiful aspect of this theory isn't its cosmic scope, but its essential humanity. Here we are, conscious beings made of star stuff, using mathematics and observation to peer beyond the boundaries of everything we can directly experience. We're asking questions about our own cosmic ancestry, wondering about the nature of our celestial parents, and contemplating our potential role as creators of future realities. It's consciousness examining its own origins in a story that stretches across infinite hierarchies of existence. The mathematical elegance that underlies this framework speaks to something profound about the relationship between mind and cosmos. The equations that describe torsion and gravitational bounce don't just solve technical problems in physics, they reveal a universe that seems almost designed to be comprehensible to conscious observers. It's as if the cosmos has arranged itself in such a way that awareness, when it finally emerges, can begin to understand the very mechanisms that brought it into being. This isn't to suggest that the universe exists for our benefit, but rather that there's a deep harmony between the structures of reality and the patterns of thought that allow us to perceive them. In a multiverse where every possible combination of physical laws gets explored, perhaps the versions that produce both complexity and comprehensibility are the ones that flourish, creating endless cascades of understanding that ripple through the hierarchy of nested realities. The observational tests that will determine the fate of this theory are already underway, their results carrying the potential to either confirm our most extraordinary suspicions or redirect us toward revelations even more surprising. The Euclid mission will map the curvature of space-time with unprecedented precision. Advanced gravitational wave detectors will listen for the echoes of cosmic bounces. New surveys will catalogue millions of galaxies, testing whether the rotation asymmetry discovered by James Webb represents a fundamental feature of our reality, or a statistical accident that dissolves under closer scrutiny. Each measurement brings us closer to an answer that will reshape human understanding, regardless of what it reveals. If we discover positive curvature in space-time, if we detect primordial gravitational waves from a cosmic bounce, if the galaxy rotation patterns hold up under intense scrutiny, then we'll have confirmed one of the most radical theories in the history of science. But even if these tests point in other directions, they'll be guiding us toward truths about cosmic origins that we can barely imagine from our current perspective. The technological advances required to test these ideas are pushing multiple fields toward revolutionary breakthroughs. Quantum computers are being developed to simulate the complex dynamics of universe formation. Artificial intelligence systems are learning to recognize subtle patterns in cosmic data that human analysts might miss. Precision instruments are being built that can detect distortions in space-time smaller than the width of an atomic nucleus. Each advance opens new possibilities for exploration and discovery. Meanwhile, the cultural implications continue to unfold in ways that touch every aspect of human experience. Artists are creating works that capture the infinite recursion of nested realities. Writers are exploring what it might mean to live in a cosmos with cosmic ancestry. Philosophers are grappling with questions about meaning and purpose in a universe that might be just one branch in an infinite tree of existence. Religious traditions are beginning to engage with the possibility of distributed creation, where creative power emerges naturally from cosmic evolution rather than existing as an external force. The educational challenges are equally profound. How do we prepare students for a future where their understanding of reality might be radically different from what previous generations took for granted? How do we teach physics when the fundamental nature of space, time, and matter might be undergoing revolutionary revision? How do we maintain intellectual humility while pursuing the most ambitious questions about existence itself? Perhaps the answer lies in embracing the wonder that drives scientific inquiry in the first place. The same curiosity that led ancient astronomers to map the movements of planets across the night sky now carries us toward questions about cosmic hierarchies and the birth of universes within black holes. The human capacity for wonder scales beautifully with the magnitude of the mysteries we're exploring, suggesting that no revelation, however extraordinary, will exhaust our appetite for understanding. The ethical dimensions of these ideas become particularly acute when we consider our potential role as cosmic ancestors ourselves. If advanced civilizations can indeed influence the properties of universes that emerge from black holes, then we might someday face the responsibility of cosmic parenthood. What obligations would we have toward conscious beings who might emerge in realities we help create? How would we balance the desire to optimize conditions for complexity and life against respect for the autonomy of whatever forms of awareness might develop? These questions push beyond traditional ethics into territory where we must consider our relationships with beings who don't yet exist and might never exist in forms we can recognize. The moral framework for such responsibilities has no precedent in human experience, yet it might become one of the defining challenges for any civilization that achieves sufficient technological mastery to manipulate the fundamental processes of cosmic birth. The recursive nature of the theory creates a kind of infinite democracy of consciousness, where every possible form of awareness eventually gets its opportunity to experience reality. In such a cosmos, we're not alone in our wonder and curiosity, but part of an endless community of conscious beings, scattered across all possible variations of physical law and cosmic structure. Some might be asking the very same questions we're exploring tonight, wondering about their own cosmic origins while remaining unaware of the infinite hierarchy that contains them. This vision transforms our understanding of cosmic loneliness and significance. The silence of our night sky might not indicate that consciousness is rare or precious, but that we're part of a much larger symphony of awareness that spans multiple levels of reality. The search for meaning doesn't end with the discovery that we might live inside a black hole. It expands into questions about our place in an infinite cascade of nested realities, each one exploring its own unique possibilities for complexity, beauty, and understanding. As we prepare to close this cosmic journey, it's worth reflecting on the extraordinary privilege of existing during a time when such questions can even be asked, let alone potentially answered. We live in an era when human knowledge has advanced to the point where we can seriously contemplate the possibility that our entire observable universe exists within the interior of a black hole in some larger reality. The mathematical tools to model such scenarios exist. The observational capabilities to test them are being deployed. The theoretical framework to understand them is being developed by brilliant minds working at the frontiers of human knowledge. Whether this particular theory proves correct or leads us toward even more extraordinary revelations, we're witnessing one of the great adventures in the history of human thought. We're not just passive observers of cosmic mystery, but active participants in the universe's ongoing attempt to understand itself through the emergence of consciousness and curiosity. The story continues to unfold with each new observation, each theoretical breakthrough, each moment of wonder that drives us to ask deeper questions about the nature of existence. We may be living inside a black hole, inhabitants of a cosmic interior that spans billions of light years, yet occupies just a tiny portion of some unimaginably vast parent reality. Or we may discover that the truth is even stranger and more beautiful than this extraordinary possibility. Either way, we're part of something magnificent, conscious beings made of stellar ashes contemplating the cosmic processes that gave us birth. The universe, through our eyes and minds and mathematical insights, is beginning to understand its own deepest secrets. And in that understanding, in that marriage of consciousness and cosmos, we find not answers that end the mystery, but revelations that open onto ever deeper questions, ever more profound wonders, ever greater reasons to marvel at the strange and beautiful reality we call home. So as you drift off to sleep tonight, perhaps you'll dream of infinite hierarchies of nested universes, of conscious beings scattered across all possible realities, of cosmic bounces that birth new forms of existence, and of the extraordinary privilege of being aware, however briefly, in a cosmos that might be far stranger and more wonderful than we ever dared imagine. Sweet dreams, fellow cosmic wanderer, and remember that in a universe of infinite possibilities, the greatest discoveries might still be waiting just beyond the horizon of our current understanding.